my dear, welcome to IMS Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, Faculty Department of Mechanical Engineering. So beta, my dear, today we'll start again the same module, but the year A are different. The year A is 2022. That means we are solving the question of related to the fluid mechanics of both branches, mechanical and civil, of the year 2022. Right. My dear, in the previous class, that means in the previous, yesterday lecture, sessions, we have to discuss all about the all questions related to the 2023. So, so you just feel it, what is the difference, how the level will change from year to year. That means how the level of this question changes year by year. So this is year 20, this is your 2022, GATE 2022. Obviously, this is mechanical. Okay. Now, my dear, what is that? see, in the question will pattern. So in this year 2022, this year little bit the questions level little. That means that is 20. This is 19. Like that. That means 1% are deviated the level of that one. That means this level is little bit what we can say that easy, little bit easy, but not that much easy. That means pattern is the same. What is that, beta? This first question pick up that in a kinematics, that means fluid kinematics. What is that? Steady. That means there is no any change in parameter, fluid parameter or any parameter with respect to time. So the 0 and the 2 dimension. Why 2 dimension? See, the function, any function, let's suppose this is any function is a relation between the x and y. That means 2 dimensional flow field is specified by the stream function. So these are the stream function. What is the stream function? This is your stream function, beta. This is your stream function. Now, this is your stream function. Now, where x and y in meter and k is constant. K constant it is given. Okay, the magnitude of acceleration. So what is, so this is a very simple problem. So only you think that if you any function, that means stream function it is given. So how it stream function will how from the stream function how we define the acceleration, how to develop the equation of acceleration. That is the main concern of this question. What is the motivation of this question? The motivation of this question is if you given the stream function, how to calculate the acceleration. My dear, we know that if the given stream function, if you differentiate with a particular direction, that means if a given stream function, if we differentiate for a particular direction, that means let's suppose this stream function is differentiated in the direction of x. This is 2 direction. So if this differentiate not absolute, partial, so dou psi by dou x. And if you differentiate with dou psi by dou y, so this differentiation gives the velocity component. This differentiation gives the velocity component, and this velocity component given in a perpendicular direction of the velocity. That means where the x and what is the velocity perpendicular to the x is v. And if the differentiation in y, so what is the perpendicular direction of the velocity in y? U. This gives, and put a negative sign of anyone. Put a negative sign of anyone, either this one or either this one. That means if you differentiate the stream function with a particular direction, that gives the velocity perpendicular to the direction. Clear? If so if you differentiate this one, if you differentiate, please differentiate this one. That means what is given? Stream function. Stream function it is given. And what is the stream function? Stream function it is given k into, what is given, beta? Kxq into y. Now if we, and the k it is given 1 meter square minus second minus 2. This is given. Okay. we have to find the acceleration. We have to find the acceleration at a point 1, 1. This is the locus it is given. Magnitude of acceleration we have to find. Okay. So what is the motivation? The motivation is that first we have to find the given this condition. This is a given condition. From this given condition, we have to find. No, wrong. You are wrong. Papa ji, you are wrong. Okay. Okay. So this is your. Now. So we have to find the velocity u. This u is equal to minus dou u by dou y, and v is equal to dou psi minus dou psi by dou y, and this v is equal to dou psi by dou x. That means if you differentiate the given function with respect to any direction, gives the velocity perpendicular to that direction. Okay. Now what is this one? So if you take this value k with respect to y, so this is minus k x q. Okay. And what is the k value? 1. So this is x q minus, and this is y. If you differentiate with respect to x, so this is your 3 k x square y. Put k is equal to 1. So this is your 3 x square y. Clear? 3 x square y. Now, so so we know that if we have a velocity, so this is a 2-dimensional. That means this is a 2-dimensional. This is a 2-dimensional. So what is the acceleration? So we have to find the acceleration. That means we have to find the acceleration in x direction and the y direction. Because this is 2-dimensional. So what is the acceleration in x direction? We know that u dou u by dou x plus v dou u by dou y. Ay we have u dou v by dou x plus v dou v by dou y. We have. Okay. This we have. Now put all this value. So you have minus xq. Dou u by dou x, dou u by dou x. So this is your minus 3x square plus what is v? V, it is your 3x square y. What is the dou u over dou y? Dou u over dou y is 0. There is no any function of y. There is no any function of y. So this is 0. How it is? This is equal to how much it is? 3x to the power 5. 3x to the power 5. And now my dear, x it is given. X it is given. What is the coordinate? This is the coordinate x and y. So put x is equal to 1. So this is 3 unit. If you put all this value in this one, so this is your also your, put this value u. What is u value beta? U is xq minus xq. And if you differentiate this one with respect to x, so this is your 6xy plus what is v? V is equal to 3x square y. If you differentiate with this one, this is your 3x square. Put all this value, so this is your minus 6 plus 9. This is your 3 meter per second square. This is also meter per second. Now you have to put what is the magnitude of this acceleration. Why? Because what is the acceleration factor? The acceleration factor is axi ayj. If you take a magnitude, a square root of this one, ax square plus ay square. Only thing is that be careful by the putting of the value of x and y. Okay, this is very important. So put this value here. What is x value? X is 3 square y is 3a square. So this is your approximately 3 root 2, and 3 root 2 it is your 4.24 meter per second. That's it. Okay, so these are the simple things. What is the motivation of this equation? So what is the expected question in the upcoming year? 4.12, right? 4.12. Okay, so what is the question you have to expect? Expect that if you have any, like that, this is the stream function. If there is a potential velocity function, this is a stream function. If there is a velocity potential function, it is given. How to find the acceleration? So from the any function it is given, how to find any another quantity, that is very important things, and you have to suppose to ask in the next year. Okay, so what is the note here? The note here is that one function is given, one function is given. From that one function, how to find kinematic parameter. Kinematic parameter. This type of question you have to, damn sure you have to practice it. Okay. Now coming to the next problem. What is the next? Next is this one. So this is the question also get 2022 ME. Now consider STD, that means this is your STD device. Consider STD. Okay, STD, that means same, no change in parameter, one dimension, that means there is only one dimension is there. Compressible flow, very important. The flow is compressible, very important. Flow is compressible. Okay, of a gas in a pipe of a diameter, the pipe diameter it is given 1 meter, the pipe diameter it is given. At one location in the pipe, the density and the velocity it is given. Density is 1 kg meter cube and velocity is 100 meter respectively. At the downstream location, let's suppose there's another location, the velocity is given this one. Okay, the velocity is given this one. The pressure drop between the two locations, that means if the fluid is flowing through any channel, but obviously the pressure will drop. Pressure will drop. Pressure will drop. So why? Because this is a one dimension, and a one dimension pipe is of a diameter 1 meter. That means the pipe of a uniform cross section. The pipe of a uniform cross section, when the fluid is flowing, the pressure will drop. So pressure will drop. That means delta P is equal to 10 kilopascal. Okay, 10 kilopascal. The force exerted by the gas on the pipe between these two locations. Force between the pipe, force exerted by the gas on the pipe between the two locations. What is the force is there? What is the force is there? My dear, this is the asking the force. That means the question is, it is dynamic. Dynamic. And one topic is force on a pipe band. Yeah, force exerted. That means this is the dynamic condition. And in this question, what the equation we will use? The equation is a conservation of momentum. What is the conservation of momentum? This is nothing. This is a force equation. That means a dynamic. So this question is related to the conservation of momentum principle. This question is related to the conservation of momentum principle. So in this one, and what is the conservation of momentum? We know that. Who gives the conservation of momentum? Newton's second law. What is the conservation of momentum? Net force on any system. Net force is any conservation of momentum. Net force on any system is equal to rate of change of A. That means mass into acceleration. That means mass into acceleration. That means mass into rate of change of velocity. That means net force, F net, force equation, F net is equal to dm dv by dt. That means this is acceleration. This is your conservation of momentum. That's it. And what is the net force? What is the net force? The net force, what is the net force? When the fluid is flowing. When the fluid is flowing, what is the force on it? When the fluid is flowing, what is the force on it? Please tell me. The force have a three kind. First one is the pressure force. Second one is the viscous force. And third one is the gravity force. First one is the pressure force. Second one is the shear force, viscous force. And third one is the gravity force. Shear force and the pressure force. Shear force and the pressure force, that means a viscous force. Viscous force and the pressure force are the surface force. And the gravity force are the body force. And the body force is exerted not by the fluid, it is exerted by the field. It is exerted by the field in which the fluid is present. In which fluid is present. That means, what is the net force on this pipe? That means there is a pipe is there. There is a pipe is there, beta. This is your pipe. Okay. This is your pipe. And this pipe, the fluid is in one direction. Let's suppose this is your x direction, axial direction. Okay. There is a one section. Let's suppose this is your one section. This is your one section. Let's suppose at section 1. And there is another section at 2. And during the fluid is flowing, the pressure drop is delta P. Delta P is the pressure drop. Okay, delta P is the pressure. All the conditions are given. So what is that? F net, conservation of momentum. Conservation of momentum. Conservation of momentum, that means net force in direction is equal to mass into dv by dt. This is your conservation of momentum, right? Okay. So, what is the force? What is the force? Force due to the pressure difference, due to the flow of the fluid. This is the pressure force. What is the pressure force? When the fluid is flowing, to maintain the flow, we must have a pressure. That means we must have a pushing kind of the force. That is the pressure force. Plus viscous force. Plus body force. These two are the surface force. Surface force, and these are the body force. Body force, and this is equal to, if you take like that, so if you write this one, so this is your mass flow rate m dot into V2 minus V1 in that direction, which direction the fluid is flowing. Okay, so this is your mass flow rate. Mass flow rate. This is your mass flow rate. What is the unit? Kg per second. Kg per second. Okay, beta. Now, so this is a precisely. Now, this condition it is given. Density at this point it is given beta 1 kg per meter cube. Velocity at this point it is given 100 meter per second. Here the velocity of V2 it is given 170 meter per second. Okay. The diameter of the pipe it is given beta. Diameter of the pipe it is given 1 meter is the diameter of the pipe it is given. Delta P it is given. How much delta P? 10 kilopascal. No problem at all. Now, in this question, they are asking that, please listen very carefully. They are asking that the force exerted by the gas on the pipe between these two sections. how the force will develop by the gas? What is the force developed by the gas? Please think this one. If there is a fluid and that fluid is flowing through the pipe, if there is a fluid which is flowing through the pipe, very important, if the fluid which is flowing through the pipe and that pipe is uniform, so on what is the origin that the fluid will develop a force, that means exerted by the gas between these two sections. So how to develop the force by the gas in between these two sections when the fluid is flowing? Which is the responsible fellow? I am telling that. Which is the responsible fellow to develop the force? Please tell me. That is the compressible flow. That's why this is given the compressible flow. If the fluid is incompressible and pipe is uniform, there is no any force will develop. Why? Because the fluid is incompressible. That means what is the incompressible fluid? The incompressible fluid is the kind of a rigid link, a rigid fluid. That means if the fluid is enter at the section and exit the another section, during this section, fluid behave as a rigid link. Now, when there is a compressible fluid, that means fluid may be compressed. So due to the pressure loss, the energy will be less as an exit as compared to the inlet. Due to this energy difference, fluid have a change. And due to this pressure drop is either compressible fluid or incompressible fluid. In both the situation, the pressure will drop. No problem. In both the situation, when the fluid is start to enter and finally it is exit, pressure must be lost. The loss of pressure due to the many characteristics. The major characteristic is the frictional loss. We are not going to detail to that domain, okay? But the pressure will loss. So pressure will loss is there either compressible or either incompressible. But the force exerted by the gas between these two sections is only due to the compressible flow. That means that Shastri. Sri Sati Kumari. Okay. Thank you, beta. So if the fluid is incompressible, that means when the fluid in, that fluid will try to compress the another layer of the fluid, and that fluid is try to compress the another layer of the fluid. During that, the force will develop by the gas. If the fluid is, so that this line is given, it is not like the beautification of the question. No, it is the logic of the question. Due to the compressible flow, the force will develop. Other than if there is an incompressible flow, so incompressible flow behave as a rigid link, there is no any force will develop. When the force will develop for the incompressible fluid, when there is a tapering is there. When there is a taper, that means flow through a nozzle. If the tapering is there, in that case the fluid will develop a force on the pipe. But if there is a uniform pipe, if the gas is compressible, there may be developed a force on the why? Because one layer will try to compress to the other layer try to compress to the other layer, so that the force will develop. Okay, so that but here, see my dear, in this situation there is no viscosity, so there is inviscid fluid, it is not given, so it is 0. Horizontal pipe, the body force is 0. Why? Because horizontal pipe, so what is that? This force and the force, that means we can write like that, this pressure force Fp, that means this is a pipe. See beta, see this one, very important information I am telling you. So this is your fluid layer. Let's suppose this is one fluid layer, this is the another fluid layer, this is the another fluid layer. Let's suppose this is the another fluid layer. Let's suppose beta, this is the another fluid layer. Okay, right? This is the fluid layer. Okay, right? Now the fluid will try to push, this fluid will try to push this fluid, fluid will try to push this fluid layer will try to push this fluid layer it tries. Why? Because we have to taking a control volume. So this flow, and finally it will exert. So this pushing kind of a force is developed by the pressure force, generation of the pressure force. Now if this will develop, and due to the pressure loss, automatically this layer will exert a force. Let's suppose this is a layer during this to this. So flow during this, this is the exit section. So this layer will try to exert a force on the pipe. So this is the negative sign. So we have to take Fp minus F, and this F you have to find. Force developed by the gas on the pipe. On the pipe, and this is equal to mass flow rate into V2 minus V1. V2 minus V1. Now, so what is this? So what is this one with a, what is the pressure force? What is the pressure force? What is the pressure force? Change in pressure into area. That means delta P into area, cross section area. This is the pressure force minus force due to the gas is equal to mass flow rate into V2 minus V1. Okay, put all this value. Put all this value. What is delta P? 10 kilopascal. 10 into 10 to the power 3. What is the cross section area? What is the cross section area beta? Diameter it is given. So pi by 4 d square, pi by 4 d square. So pi by 4, that is 0.25 pi minus this force F. What is the mass? What is the mass is there? So we have to find the mass flow rate. What is the mass flow rate? What is the mass? Density is equal to mass by volume. So if you find the rate, so this is rate, that means mass flow rate is equal to density area into velocity. So density you have, area you have, density, this one, 0.1 pe, rho 1 and V1. So mass flow rate at 0.1, the same mass flow rate is there. Mass flow rate inlet and mass flow rate exit is same. So mass flow rate inlet rho 1 it is there 1, area it is there. What is the area? Area it is your pi by 4 d square, d is 1 into what is the velocity? Inlet velocity is there 100. So if you calculate, this is your 25 pi in the sense of pi. So we have to put here 25 pi into what is V2? V2 it is your 170, V1 is 100. So if you try to find the force it is your 750 pi Newton. So option it is given in the pi form. So 750 Newton. This is your 750 Newton. Okay, clear? So what is the motivation of this question? How to apply the momentum equation for the given situation. So this equation you have to remember, momentum equation. This is the conservation of momentum principle. This is the conservation of momentum principle, and that conservation of momentum, if you define that, this conservation of momentum principle have to develop in the fluid mechanics of a two kind of equation. First is Euler's equation, and second is Navier-Stokes equation. Navier-Stokes equation, and these two are the force equation. Momentum, that means force equation. These two are force equation. These two are force equation. That means we have to balance the force. It is not energy equation. It is a momentum equation. This is your momentum equation. Okay, great. Now we have to go to the next problem. Please read this question, beta. This is also a good question is there, but little bit there is a calculation lengthy. What is this? See beta, this is so this question is related to the drag. So this is the question asked in the mechanical department, but you may be a very damn sure this type of question may be asked in the civil department. Why? Because in the civil department, the drag and lift is very important. Drag and lift is very important in the civil department. So this is your also 2022 mechanical. Okay. Now, see, so this question is, so drag and lift, in which contents you have to read in the fluid mechanics? Boundary layer theory. Boundary layer. In this context, in this chapter, we have to study the drag and lift. So what is that? A solid spherical ball, a solid spherical lead bead is there of lead, which material? Lead of uniform density. That means this solid spherical ball of a density it is given, and a diameter it is given 0.1, very minimum diameter it is given, sink with a constant velocity. That constant velocity is same as known as a turbulent velocity. That means there is a sphere is there, and you have to put the sphere in the stagnant pool of the liquid of a dynamic viscosity, this one. That means there is a liquid is there, you have to pull. That means there is a large amount of the liquid, and that liquid have a viscosity it is given, and you have to simply drop this spherical ball into that liquid reservoir, and it will be sink. That means it will be moved downward through a velocity v. Okay. The coefficient of drag, that means if you, so let's suppose you have to try to jump. So when you jump when you are jumping inside the fluid, there must be a drag force. Okay. So the coefficient of drag it is given, and this coefficient of drag it is 24 by Reynolds number. It is given, where Re, the Reynolds number, is defined on the basis of a diameter of the bead. So this is your Red. That means Reynolds number we have to define on the diameter basis. The drag force acting on the bead is experienced. This is your drag force. So drag force acting on this bead of the sphere. So this equation it is, see beta, sometime you have to remember this equation. What is this equation? Simply, what is this one? Drag force, we know that Fd is equal to drag coefficient into half rho v square into area, cross section area. This is given, and we know this relation. So this we have, where rho is the density of the liquid. Neglect the buoyant force. Why we have to neglect this buoyant force here? Anyone, please? Why we are neglecting the buoyant force here? Please, anyone? Why here we neglect the buoyant force? Anyone, please? Reply in the chat box. Why we are neglect that? This is not a beautification or anything is there, but this is the logic. Why? Because this body, this bed, the spherical body have a very, very, very small dimension. Why? Because the drag force is responsible due to the volume displacement. Higher the higher volume displacement, higher the buoyancy force. Higher the higher volume displacement, higher is the higher buoyancy force. So the displacement of the fluid is very minimum. Why? Because the diameter is very low. So on this context, we have to neglect the buoyant force. Okay, and acceleration of due to gravity is given. Then what is the velocity? We have to find it. Now, my dear, what is the drag? So drag force, always keep in mind, a student get confused here. Why this? Drag is always, so beta drag, okay. So drag, the drag it is a kind of force. So the drag it is a kind of force. A force have a direction. So in which direction the drag will act? Motion direction. That means drag always acts in the motion direction, like the shear stress. Previously we have to study that there is a flat plate is there. Over the flat plate the fluid is flowing. Always remember, don't confuse with that. If this is your flat plate and the fluid is flowing here, so obviously on the plate the shear stress is like that. Yes or not? Shear stress is like that. So this shear stress acting along the flow direction. So this shear stress due to this shear stress, wall shear stress, so stress is what? Force upon area. So if you multiply with this shear stress to the area of this wall, exposed area of the wall, automatically that gives the drag force. So drag force is the same direction as the shear stress. So drag force always in the motion direction. Motion direction. In the motion direction. So note point is there, note. Drag force acts in the direction of motion. In the direction of motion. Number first thing. Next thing, what is the drag force? We have to denote FD or simply sometime D. This drag force is equal to it. See, drag coefficient is what? Drag force divided by dynamic force. A dynamic force, it will convert, think about in the dynamic, it is kind of half rho V square. So drag force is equal to CD drag coefficient into half rho V square into, so this is your, and into we have to multiply the which area? Projected area. Projected area. Yeah, exposed area. Now my dear, so what is the projected area? That means area of the body, area of the body on a plane perpendicular to the direction of flow, to the direction of flow. How it will assume like that? How it will assume? This is your beta ball, and let's suppose this ball is moving in this direction. So the area, so the drag force, ball is moving in this direction. So the area is this one. This is your projected area. Okay, so on this area the drag force will act. Okay, now this is the projected area. And what is this one? This is your dynamic pressure. Dynamic pressure. This is your dynamic pressure. Now here mu it is given 1.1 cross 10 to the power minus 3 kg per meter second. Here the buoyancy force is equal to 0. Why? Very small body. Very, very small body. Okay, so that the buoyancy force is neglected. Let's suppose W is the weight. Now beta, this will put into the container. Okay, this will put into the container. Great. So this is your weight. This is your weight. W, this is your weight W. Okay, so the fluid is at rest, body is moving, so obviously the drag force is upward. There is a drag force Fd, and also there is a buoyancy force Fb. Other than that, there is no any velocity. Okay, any things. So okay, now so we have to take a equation of motion, that means the net force on this one, and this is uniform. This velocity is uniform. This velocity is uniform. So what is the net force? F net is equal to mass of the body into acceleration. And what is the acceleration? Mass into dv by dt, and this is uniform, so it is 0. So net force on the body is 0. Net force on the body is 0, and the net force, it is in y direction. We have to adjust it. So downward we have to take let's suppose downward is W. Let's suppose downward we have to take negative, upward is positive. So what is the net force? Fd minus buoyancy force, Fd plus buoyancy force minus W is equal to 0. Okay, is equal to 0. Now here in the question it is given the buoyancy force, it is 0. So what is that? Drag force is equal to weight of the body. This is my standard equation. That means the equation is applicable in this situation, right? So we have to find drag force. Simple. We have to find the drag force, then we have to find the weight of the body, and we have to equate with that and find this velocity. Find this velocity. So what is the weight of the body? We have to find first weight of the body. Weight of the body, W. So what is that beta? Density is equal to mass by volume multiply with G. So this is what? Body weight. So what is the weight of the body? Density of the body, G, and the volume of the body. Yes or not? Yes or not, beta? We can write like that. And yeah, you can say like that also. And you can also, this is a weight, and we can also like that. We have to find also rho G into V. What is the density we have? Density of the body we have. Let's suppose the density I have, why? Because body have a material, the body material we have, we know the body material. According to the material, we have to know the density. That means density is the property. And volume. So this volume of the body and the volume shape is a sphere. So what is the volume? 4 by 3 pi RQ. Yes or not? 4 by 3 pi RQ. Now 4 by 3 pi RQ, and the diameter it is given. So instead of diameter R, we have to put D by 2. Yes or not? D by 2. So rearrange like that. And now, so first job is finished. Now we have to find, so in this one, if you find, sorry, if you find, sorry beta, if you find the drag force, so we have to find the drag coefficient. Once we have how to find the drag coefficient? We have to find the drag coefficient is equal to 24 by the Reynolds number based on the diameter D. So first we have to find the drag, coefficient of drag. So this is okay. We have to find the weight, and now for this one we have to find coefficient of drag CD, and this coefficient of drag, it is given 24 by Reynolds number, and this Reynolds number based on diameter of the body. So RED. Okay, so what is RED, beta? What is R Reynolds number based on diameter? So this is your external flow, yes or not? That means body will sink into the fluid, that is your external flow. That means we have to write rho, and this velocity, uniform velocity V into diameter of the body divided by this viscosity. Now we have to arrange like that. This is your body. So so this is your rho into V we have to take, and D by D we have, one second. So this is your rho into V we have to take like that. This is your volume. Now what is the diameter? 0.1 cross 10 to the power minus 3. What is the kinematic viscosity? It is given 1.1 cross 10 to the power minus 3. If you rearrange like that, so this is your rho V by 11. Okay, so this is your Reynolds number. So what is the drag coefficient then? So if you put reverse this one, so this is 24 into 11 divided by rho into V. This is your drag coefficient. Okay, this is your drag coefficient. Clear? Now this is your drag coefficient. Now my dear, so we have to arrange. So what is the drag force here? D it is given. What is the drag force? It is the relation, it is given, beta. The relation it is given, and otherwise we know also. This is given in the question. This is given. CD 0.5 rho V square pi by 4 D square. This is why? This is the projected area. Yes or not? This is your projected area. See this one? Projected area very important. So what is the projected area of this one? This is your projected area. Projected area is there. So fluid is flowing. So what is the projected area? This is the projected area. So in the drag, we are not calculating the cross-section area. We are not calculating the perimeter. We are calculating the projected area. If you calculate the drag, okay, if you calculate the drag, and if you calculate the buoyancy force, so what is the difference between drag force and buoyancy force? If you calculate the buoyancy force, we have to calculate the volume displaced. Volume displaced, and displaced volume is what? Displaced volume is what? Total surface area into length. If there is a cylinder is there, we can say that cylinder. What is the displaced volume of the cylinder? Total area, surface area into the length. So here if you calculate the buoyancy force, the area is responsible to the surface area. But if you calculate the drag force, the area is responsible to the projected area. Very important. The area is projected. So always remember like that. This thing is always remember. If you calculate the drag force, we have to take the area is projected area. If you calculate the buoyancy force, we have to take the area of a surface area. Clear? Okay. So now what is the drag? So drag it is given, beta. We have to write this one. So CD, we have to write this one, CD half rho V square into area pi by 4 D square. Here is the sphere, so the projected area itself is a cross section. So we have to all put all this value. What is the CD? 24 into 11 divided by rho into V. V is the velocity, very important. Sorry, V is the volume here. V is the volume here, okay? V is the, no, V is not a volume. Sorry, this is not a volumeter, very important. This is not a volume. This is your velocity, okay? This is your velocity is there, okay? V is the velocity, V is the velocity. Now, okay, no problem. Rho, V, silly mistake is there into V. So this is your CD. This is your CD, correct? Now, in this one, half rho V square, okay? Here, we have to write pi by 4 d square. So this is your drag, and this drag is equal to weight. And what is the weight? What is the weight? If you calculate this, convert into weight. What is the weight? If you write all this one, density of the body it is given, g it is given, volume in the form of diameter, if you write this one, so this is 132 into velocity into pi by 4 d square. Okay, pi by 4 here, pi by 4 d square we have to take outside. Okay, so from this one we have to neglect something. Okay, now this is okay. 1 second, we have to check. 24 into 11 by rho d into 0.5. Okay, correct. Rho v square pi by 4 d square is equal to 32. 32 v d square. Okay, no problem at all. No problem at all. This is not like that. Okay, no problem. Now, so 4 by 3. It is your. If you calculate this one, 132 half you have to done. So this is there. This is there. Now this is equal to the weight of the body. So what is the weight of the body? 4 by 3 pi d by 2 ka q rho into g. Okay. Now we have to apply the equation. What is the equation? Weight of the body is equal to drag force d. Okay. What is the weight of the body? Rho into g, you have to take volume of the body 4 by 3 pi d by 2 cube, clear, is equal to this one drag force 132 into v into pi by 4 d square. That's it. That's it. Now all the things you have, diameter you have, only unknown is velocity. So if you rearrange this one, so these are the little bit calculation. Okay. So if you rearrange this one, this v is equal to rho g d divided by 6 cross 33. Now rho you have, what is the rho? Rho you have 1100 000 into g is 10, it is given, into diameter 0.1 cross 10 to the power minus 3. Why? Because it is given very less diameter. 6 cross 33. If you solve this one, this is your 1 by 18 meter per second. The option, it is in the ratio form, so it is there. Clear? This is clear, beta? Simple calculation is there. Okay, simple calculation is there. Okay, so first we have to, so what is that condition? We have a condition, weight is equal to drag force. So just we have to first simplify the drag force equation by putting all the value. We have to simplify the weight equation by putting all this value. Then we have to equate one, and what is they are asking, we have to find it. So simply these are the calculation. There is nothing is that. One concept is there. If you calculate the drag force, so the area is responsible to the projected area. Okay. If you calculate the weight, if you calculate the weight, if you calculate also the weight, if you calculate the weight, so weight is the area, body is the volume. Volume, you have to equate the volume. If you calculate the buoyancy force, the buoyancy force volume is the displaced volume. So who is the responsible to displaced volume? Surface area. Who is the responsible to the displaced volume? Surface area of that. So buoyancy force responsible to the surface area, drag force responsible to the projected area. This is very important. Okay. Now the next one is that, next one is a very, very good problem is there. This is very good things. Now, why we have to take intuitionally? Why? Because see this one. Why? Because this is the, see, in the compressible fluid, we have to only solve the numerical type of problem. What is the what is the Mach number, what is the temperature, what is the velocity, what is the sonic velocity, what is the sound velocity, all the things. But these are the theoretical questions in which the hard code, in which we have to discuss with the back pressure, we have to discuss with the normal pressure. When, if you change the back pressure, what is the changing at that, this is the minimum area of this nozzle, so that is called throat. So at what condition, what is the condition at the throat when the, if we change the back pressure? So what is given, figure show purely conversion. That means, see, there are three conditions is there: pure conversion, pure divergent, and convergent and divergent both at a time. So this question is related to the pure convergent nozzle with a steady inviscid compressible flow of ideal gas. See, steady is there. There is no any parameter which change with respect to time. Inviscid, that means there is no any shear stress is there. Compressible flow, that means density will change of an ideal gas, right? With a constant thermophysical property, that means thermophysical, that means what is the thermodynamic property? There doesn't change. Operating under the chalked condition, very important. Operating under the chalked condition. What is the chalked condition, beta? Operating under the chalked condition. What is the chalked? What is the chalking is there? We will discuss, no problem. The exit plane, so this is the exit plane. This exit plane shown in figure is located within the nozzle. So these are the nozzle, that means it is not within the tank. So within the nozzle, this line is very important. If the inlet pressure, this is your inlet pressure. That means this pressure, due to this pressure, the fluid is tried to in. So this is your inlet cross section. The inlet pressure P naught is increased. So this, we have to increase this inlet pressure. What is the condition? From here, the condition it is given. The exit plane, okay? If the inlet pressure, this is the condition, is increased while keeping the back pressure unchanged. That means this back pressure is fixed. We have not changed. Back pressure is not changing. Which of the following statement is true? My dear, the statement it is given is RR. That means this is your MSQ type question. Okay? More than one option is correct. Mass flow rate through the nozzle will remain unchanged. Number first, whether the mass flow is changing or not. Mach number at the exit of the plane will remains unchanged at unity. That means if whether the Mach number is unity, that means it will not change. Mass flow rate through the nozzle will increase. That means if you do the activity, the mass flow rate will increase or not. Mach number at the exit of the plane nozzle becomes more than unity. That means either it is greater than 1 or equal to 1. Mass flow rate m dot will constant or m dot will increase. They are asking like that. During this condition, when inlet pressure will increase while the back pressure is fixed. What is the condition? Clear? This is clear, beta? Okay. What is that? See this one. It is visible? Yes, it is visible. So this is your convergent nozzle. This is your convergent nozzle, beta. This is your convergent nozzle. Okay. This is your convergent nozzle. Okay. This is your convergent nozzle. This is your nozzle. Clear? This is your nozzle, and that nozzle is converging type. This nozzle is a converging type. This nozzle is a converging type. This is the nozzle at exit. This is the nozzle at inlet. At this pressure is P naught. Okay, and this is your exit pressure, and here there is a back pressure, and this back pressure is constant, and this inlet pressure will increase, changing. Okay beta. Now see this one. There is a P naught pressure if it is constant. If the pressure throughout constant, obviously if this is your nozzle and it is act as a control volume, it is act as a control volume, this nozzle act as a control volume. So if this pressure is constant, let's suppose number first condition, case number first, no flow, yes or not? There is no any flow, yes. Okay, sir, if the pressure throughout constant, that means what is the pressure? That means this pressure is constant throughout, no flow is there. Great. So if there is a no flow, that means during that no flow, mass flow rate is 0. So at one condition, there is no mass flow rate. Yes, there is a no mass flow rate. So that is at point 1. So at point 1, this P naught is the maximum pressure. So that during that there is no any mass flow rate. So mass flow rate is 0 when P is constant. Clear? Mass flow rate constant when the P is, so mass flow rate is constant when the P, so mass flow rate, so no sorry, mass flow rate is 0. So at this one, no flow, that means mass flow rate is 0, not constant, it is 0. So at this condition, at point 1, mass flow rate at point 1 is 0. Clear? Now my dear, if we decrease the pressure, that means if we decrease the pressure, so if we decrease the pressure, let's suppose this is P star, so there is a sonic flow. If we decrease the pressure, let's suppose this is P star, at that point there is a sonic flow. My dear, at a sonic flow, so very important, sonic flow Mach number is equal to 1. That means flow is there, but the flow is sonic. Now my dear, when the pressure will decrease, during the converging part, when the pressure will decrease, where the pressure will decrease? The pressure will decrease when there is at throat. That means at a throat, this is your minimum area. So at a throat, there is a minimum area. That means velocity is maximum. Let's suppose velocity is maximum, pressure will reduce. So at that condition, the pressure will reduce. That means when the pressure, that means at the pressure will reduce. Where the pressure is reduced? At the throat. So at the throat, the pressure is reduced. So at the reduction of that pressure at the throat, the flow is sonic. And for the sonic flow, the Mach number 1. That means, my dear, one option is very clear that, sir, what is that? Sir, Mach number at the exit plane, that means at the throat of the nozzle will remain unchanged at unity. This option is correct. Why? Because if the pressure will drop, the flow is sonic, and during the sonic flow, the Mach number is 1. So the option B, first option B is correct. Okay. So option first B is correct. Now we have to check the next option. Why? Because this is the case of MSQ. So we are more than one option correct. Now Mach number 1. Now we have to check if the back pressure, that means if the inlet pressure increase, what is this mass flow rate? What is this mass flow rate, beta? whether the mass flow rate will increase or decrease. Please check that whether the mass flow rate is increase or decrease or constant. What is the option if we increase this one? Now my dear, see this one beta, if this is at a sonic condition, that means at the exit plane, the Mach number 1. Why? Because the pressure will reduce. The pressure will reduce, so the Mach number 1. Now my dear, let's suppose we have to increase this pressure. We have to increase this pressure. Now, one second. We have to increase this pressure. We have to increase this pressure. Now, for the given, see, what is the choking condition? The choking condition, first option is clear. Now, expansion of the wall. There is a exit section, there is a wall, and if you expansion of the wall, that means if you open the wall, if when there is a valve is there during the expansion of the wall. So during the expansion, pressure will reduce. Pressure again reduce. So pressure again reduce. So this is the condition. 1, when there is a no flow. 2, subsonic flow. So there is a sonic and no flow. Between that there is a subsonic flow too. So subsonic flow again. Why? Because there is a choking. Choking is when there is a choking. That means if you change the pressure, the mass flow rate doesn't change. Okay. Now for the expansion 4, the expansion and sonic flow. For the expansion and sonic flow, the mass flow rate is approximately maximum at that point. So if we decrease the pressure, see my dear, if we decrease the pressure, now if here it is increase the pressure. Now if we increase the pressure, see, if we increase the pressure, increase the pressure, the mass flow rate will decrease. But what is this condition it is given? Here mass flow rate through the nozzle will increase or constant. So constant it is not. So this option is wrong. There is no any constant. When there is a constant, there is a maximum. That means unchanged. When there is a choked, so the figure has convergent dimension. The choked condition, that means thermophysical property operating under the choked condition. That means choking is a compression. So what is the choking beta? Choking is a compressible flow effect that obstruct the flow. That means we have to obstruct the flow. That means we have to increase such a back pressure is higher and higher so that the flow is never will be happen. That is called choking. That means flow is never happening. Choke is a compressive flow effect, that obstruction of the flow, setting a limit to the fluid velocity. So there is a limit of the fluid velocity. It is because of the flow becomes supersonic and cannot. So when there is a supersonic moving in the upstream. Now nozzle choke is a dynamic condition. This is a dynamic condition of a fluid when a fluid flow at a given pressure and temperature through the throat of a nozzle into the low pressure environment, the fluid velocity will increase. Yes, the fluid velocity will increase. For a given configuration, the convergent nozzle with steady inviscid compressible flow of an ideal gas, the Mach number at the exit plane at the throat in a converging diverging nozzle remains unchanged and unity. This is option correct. Now, under the choked condition in the nozzle, the mass flow rate through the exit plane will the first increase. Yes, under the choked region, this is choked region, first increase. Yes or not? This mass flow rate is first increase now. First increase. So under choked condition, this is a choked condition. So first in the choked condition in the nozzle, the mass flow rate through the exit of the plane will first increase and then becomes maximum during the choked condition. So it will increase. It will never decrease and then constant. That means mass flow rate will increase, then it is constant, and that constant value is maximum. So what is the option increase. So option C is correct. So B and option C. Clear? Clear? This is clear? Okay? This is clear now? Now, so next one is this question. This is also good question, is 2022. This is a different set is there, beta. Consider a steady flow. The steady flow, that means the property doesn't change with respect to the time. Horizontal divergent. This is a horizontal plane divergent channel. This is a divergent. Previously is convergent, and now this is a divergent. As shown in figure, with a supersonic flow, that means the flow is supersonic flow at the inlet. Let's suppose this is at inlet, and at here supersonic flow. Supersonic flow at the inlet. The direction of the flow from the left to right, this is the direction of the flow from left to right. Pressure at the location B, this is the location B, is observed to be higher than the upstream. This is upstream and this is downstream. If the fluid is flowing beta from A to B, so this is your upstream, that means the location B observed higher than the upstream location, that means this is your upstream and this is down, and this pressure higher than this upstream. Which of the following conditions can be reason? What is the reason? What is the reason? Since the volume flow rate is constant, velocity at B is lower than velocity at A. Number first, normal shock, viscous effect, boundary layer separation. See, we all know that if there is a divergent, there is a boundary layer separation maybe. But whether this option is correct or not, the viscous effect, normal shock, since the volume flow rate, yes, volume flow rate is same, the velocity of B is lower than velocity at A. Yes, during the divergent, but when the, here the pressure is, what is the, here the velocity is high, here the velocity is low. Why? Because pressure is high, area is maximum. But this is due to the incompressible fluid, not compressible. Compressible fluid we have to decide with the Mach number. Okay, so see this one. We have to discuss this thing. What is that? See this one, beta. So there is a nozzle like that, diverging part. This is point number A. This is point number B. Okay. Okay. This A is supersonic. Supersonic flow at this point, that means Mach number is greater than 1. Okay, so horizontal diamond channel with a supersonic flow at inlet. So what is that? Given horizontal divergent channel with the supersonic flow at inlet. Inlet, that means Mach number is greater than 1. If this is there, we have to prove that. Just now we have to prove that the condition of this is the condition of normal shock. Why? The question mark is there. We have to derive it. Why? We have to derive it. Okay. See beta, the pressure, obviously here, the pressure here, obviously the pressure at B, it is given in this condition कि pressure at the location B is observed to be higher than the pressure at A. That means pressure at B is higher than the pressure at A. Okay. So velocity at B is less than velocity at A. Okay. So since the volume pressure, so velocity at B is lower than velocity at A. Velocity of B is lower than velocity of A. This is correct, but reason is not correct. This is very important. I'm telling you, maximum student get confused here. First one is that since volume flow rate is constant, no volume flow rate. How we can say that the volume flow rate is constant? Why? Because this is the compressible flow. So reason this line is correct. The velocity at B is lower than velocity A is correct, but this line is wrong. It is not, since the volume flow rate is not constant. Okay. That means velocity at B, this is okay. Now, so adverse pressure gradation will cause the flow separation. So here PB is greater, so flow separation is there. Okay, but since see, so dA, what is the Bernoulli equation in this case? dA by A from the Bernoulli equation, dP by rho V square into 1 minus Mach square. This is okay, equation is there. Since here PB is greater than PA, that means PB, this is positive. Area change is also positive. Yes or not? So this positive quantity, so this is also positive. So if this is a positive, M is greater than 1. No, M is less than 1. So at this condition, M is less than 1. Very important. See this one. PB, that means delta P is positive, divergent, delta A is positive. So if this is also positive, this is positive, this is also positive, this is positive. So 1 minus M square is greater than 0. That means M is less than 1 at this section. So at point B, the M is less than 1. That means if M is less than 1 at point B, M is less than 1 here, that means sonic flow. No, that means subsonic flow. Yes or not? Now, my dear, if the flow from supersonic to subsonic, there must be a normal shock. If the flow between supersonic to a subsonic, there must be a normal shock. This is the condition. So the option is A is correct. So hence, what is the note point is that? The note point is that flow supersonic to subsonic that is the condition for the normal shock. So option is C. C is correct option. Clear? C is your correct option. So this is the simple problem, but there is a very logical things. Now we have to take the next one. This is a very simple problem. This is very simple, very simple, very simple, very simple, very simple, very simple question is there. This is also, but this is important. Simple, but this is important. What is that? The velocity field it is given. This is the velocity field in 2 dimensions. Which of the following statements are correct? MSQ type question, okay? The velocity field is 1 dimensional. See, this is very wrong. No, it is 2 dimension. The flow is incompressible, compressible, we have to check. So my dear, the flow, there is a condition you always remember for that one. There are many more conditions is there. There are many more conditions are there. What is that, beta? If the flow, if for the compressibility or incompressibility, for the compressibility for or incompressibility, we have to check the continuity equation. That means del dot V. That means we have to check del dot V. So we have to check del dot V vector. This we have to check. If this is 0, if del dot V is equal to 0, if this is 0, then this is your incompressible. The flow is rotational or irrotational, we have to check. So this the velocity component, this U and this is your V, it is given. So U and V given, so the rotation or not, it is along Z direction. If U and V it is given, the flow is rotating or not, so we have to check in the Z direction. So we have to check omega Z. If the omega Z it is 0, that means not rotation. That means in the Z plane, in the Z, sorry, not plane, in the Z direction, the fluid is not rotating. Okay, so the flow is irrotational. Now, the acceleration experienced by the fluid particle is 0 at a point x. That means that next you have to find the acceleration at a location 0, 0. Simple problem is there, very simple is there. So we have to check one by one. So these are simple problems. You have to, okay, you have to try to solve by yourself. Please put the comment here. So if you want to solve, I want to solve. So given is what? Given. What is the velocity? Velocity function it is given by V. This is the velocity field. What is given? 4xy I plus 2x square minus y square j. Clear now? So here this is in the form of like that ui plus vj. So here u is equal to 4xy and v is equal to 2x square minus y square. Okay. So we have to check del dot v vector. We have to check del dot v vector. So del dot v vector, del operator. So what is that? Del by del x. Del by del x. So this is u. You can say that u component plus dou y of v component. That means this small v. If you check this one, if you put this value, this is 4y minus 4y. If you differentiate, this is 0. That means flow is incompressible. Incompressible flow. Right. So incompressible. Number second, rotational. You have to find omega z. So for the rotation, 1 by 2, always remember opposite sign. That means, right, if dou v, yeah, you can write here. How to write? Dou x minus divided by dou y. If there is a y, here dou v. If there is a x, here dou u. Like that you have to remember. Cross it. This cross it. This cross it. Okay. Now put this value. If you put this value, this is also 0. Okay. Now third one is the acceleration. So acceleration is also, if you find the acceleration, right, because u and v you have. So if you find the acceleration, acceleration is also 0. So this fluid is 2-dimension. the fluid is two-dimension, incompressible, irrotational flow, with zero acceleration. This is okay. Clear? This is clear, beta? So this is the kind of the fluid. Now the next one is also very simple. Pitot tube, related to pitot tube. What is the difficulty in here? We have to take a datum, that means from this one. This is your free surface. That means, see with this one, beta, liquid stream is there. This is the liquid stream. And this liquid stream is up to that, and pitot tube is up to here. And this H2 is given, H1 is given, atmospheric pressure is given, and they are find that volume flow rate through the pitot tube. Simple question is there. Volume flow rate through the pitot tube. See, my dear, this is your H1 height, this is your H2 height, this is the velocity. Okay, so so how to find the velocity? So this is your velocity. If this is your velocity, that means you have to take, this is your streamline. This is your streamline. One fluid is moving. This is your streamline. So we have to apply the Bernoulli equation through this line. This is 2 point. This is first point. That's it. So here the velocity it is given, volume flow rate through the tube. Volume flow rate, that means discharge. You have to find discharge. Okay, you have to find discharge. Please find it. So we have to draw. This is your pitot tube. This is your pitot tube. This is surface. Okay. This is your stream at this point. This is a fluid stream. Okay, this is a fluid stream up to this section, and up to that one there is atmospheric pressure. That means this is surrounding. And at that surrounding there is a atmospheric pressure. So here there must be a P atmospheric. Okay, there is a center line, and the height, all the heights are given. From this one there is H1, up to this one there is H2. Okay, H1 and H2 are given. We have to change the color here. This is very bad color, I think. Okay, so this is H1. This is H1, and this is H2. I think H2 is, it is not like that. H2, it is above then. It is not H2. H2 is from here. This is H2. That means vertical height of the pitot tube is H1 plus H2. Okay, no problem at all. Now, atmosphere. Apply the Bernoulli equation between this point 1, this point 2. You have to find the discharge. That means there must be a flow is there. That means P1 by rho G plus, if you take this, this is at a reference level. Let's suppose this is our reference. So at this point that there is no any potential, only velocity is there, v1 square by 2g plus potential is 0 is equal to, at this point, 2 point p2 by rho g plus v2 is there by 2 plus v2 upon g plus height. This is a height now. So h1 plus h2 from the datum line. Clear? What is P1? What is the pressure at this point? What is the pressure at this point? Pressure due to this fluid plus pressure due to the atmosphere. So P ATM up to this point plus rho g height h1 divided by rho g plus v1 square upon 2g. What is P2 beta? P2 is atmospheric pressure by rho g. V2 is there 2g plus h1 plus h2. Clear? So this atmospheric pressure by rho g, this atmospheric pressure by rho g, it is cancelled out. So this is your beta. Okay, h1, and there is your, here h1 is there plus v1 square upon 2g is equal to v2 square upon 2g plus h1 plus h2. Again h1 cancel out. Why? Because this h1 is common for this one and this one both. So h1 is common. From here we can find easily v2. What is v2? Root under v1 square minus 2g h2. 2g h2. This is your v2. Exit velocity. So find the discharge. What is the discharge? Volume flow rate. That means discharge is area pi by 4 d square into the velocity v1 square minus 2g h2. That's it. That's it. Okay. Clear? Simple problem. Now, the next problem is very important. This is the next problem, which is very important problem. What is that? This is very important question. What is that, beta? The steady velocity filled in a inviscid fluid. The fluid is inviscid. That means there is no any viscous effect is there. Inviscid. Fluid is inviscid. That means viscous effect is 0. Viscous effect is 0. Density it is 1.5. Is given to be the velocity field it is given. Velocity field it is given. Neglect the body force. The pressure gradient at this one. This is very wrong. Pressure gradient. Pressure gradient. That means del P. Pressure gradient you have to find. Del P. Now, my dear, this is your gradient of the pressure. You have to find. How to find number first question? You have to find this question when you have to find this question. How to find? You have to find the pressure. That means pressure gradient. That means a fluid dynamics. Number first. Which equation is applied? Either the Euler's equation or the Navier-Stokes equation. That means conservation of momentum. Fluid dynamics. That means conservation of momentum. So we have to apply for this one. Velocity field it is given. So in the general, what we know that we have to take in general equation of the conservation of momentum. What is that? See, conservation of momentum of momentum What is the conservation of momentum? What is the conservation of momentum? The conservation of momentum is like that. See this one. What is that? Net force into mass into acceleration. So acceleration we have to write in the material form. Acceleration, that means rho dv by dou u by dou t is equal to minus grade of P plus mu del square U vector plus rho into G vector. Clear? Now my dear, this equation is what? Conservation of momentum equation. This is your conservation of momentum equation. What they says that? They says that the net force, this is the force due to the pressure, due to the force due to viscosity, and this is the body force. So this is the body force, this is the surface force. Surface force due to the viscosity and surface force due to the pressure. So this is called pressure gradient. So pressure force, viscous force, body force. So this is your, one second. This is your body force. This is your body force. Body force. This is your viscous force. This is your viscous force. And this is the pressure force. Pressure force. This pressure force is due to the fluid flow of the fluid. This is viscous force due to the viscosity of the fluid. This is the body force due to the gravity. That means the field. This force will exerted by the field of the fluid. Field in which the fluid is operated. And this is your acceleration. Acceleration. That means this is your mass into acceleration. Kind of this thing. So net force is equal to mass into acceleration. That is the force equation, and that is the conservation of momentum. Now my dear, what is this one? If you write only this thing, this one, this is called material derivative. Or called total derivative. And if you write total, this one, this we can write like that. If you split this total, so this is your for local plus temporal. This is for the local plus temporal. So this rho dou u vector by dou t, this is your temporal, plus rho u vector into del into u vector. So this is your temporal, this is your local. That is the total combined. This is a space coordinate, this is a space derivative. That means this is a position, this is due to position, and this is due to the time. And if you add this total derivative, that is called the, if you add this two derivative, that is called the material derivative or a total derivative. Clear? If you add this to this one, this is called material derivative or total derivative. Now my dear, what is the question it is given? The question is given steady. That means the parameter which is changed, this steady, that means this is 0. Why? Why? Because steady. Clear? Now next one is inviscid. That means this is 0. Why this is 0? Inviscid. No viscosity. Now, again this is that is given by neglecting the body force. That means this is also 0. No body force. No body force. There is no any body force. So what is the equation now? So equation will convert it into very concise manner. What is that? Rho u dot del into u vector is equal to minus of grade P. My dear, I ask one question. This is the force component, this is the force component, this is the force component, this is the force component due to the pressure difference, this is the force component due to the viscosity of the fluid, this is the force component due to the weight of the fluid. Okay. Now, this force component is positive, this force component is positive, but this force component is negative. Why? That is our question. This force component is negative. Why? Why this is negative? Why? Because this is the pressure gradient. Pressure always, that means the fluid is always flowing from higher to lower. That means this represent higher to lower. That means decreasing. So for the decrement, you have to multiply minus so that it will positive. So this is a gradient of the P. The gradient of the P, the direction is always higher from lower. So from higher to low, this is always, this is your weight, this is your weight, but this is the pressure gradient. That means the pressure gradient, that means change in pressure. When the change in pressure, when the fluid is flowing, if the change in pressure is there, that means the fluid is flowing from high to low. For that one, high to low, we have to take a negative sign. Clear? So this is, now what is the grade of the P? What is the grade? This is a two-dimension fluid, yes or not? These are the two-dimension fluid, x and y. So grade of the P in the two-dimension. What is the grade, beta? We know that del of operator, del is what, beta? Dou by dou x plus dou by dou y. This is your grade. This is your grade. So grade of P is what? Del P by del x, del P by del y. Now this is the acceleration term. So here del P by del x, when you have to find del P by del x, del P by del x, that means x component, that means we have to find the acceleration in x component, and that x component of acceleration is only the local, not temporal. And then you have to find the grade of the P in a y direction, and that y direction, that means acceleration you have to find in y direction. So you have to find the acceleration in x direction, y direction, put the value, separate this one, find the pressure. Clear? So what is the x direction? If you split these two equations into the x and y direction, how to write, beta? This is very important. So if we write in x direction, how to write? How to write in x direction? See, rho it is there, rho it is there. So rho in x direction, u dou u by dou x plus v dou u by dou x. Dou u by, sorry, not dou u by, v dou u by dou y. U v dou u by dou y. This is your, and what is the pressure in the x direction? Minus dou p by dou x. Clear? So this is the acceleration. This is the Navier-Stokes equation for this corresponding equation in x direction. Now, what is the y direction? What is the y direction, beta? Y direction. Y direction. Put y direction, what is that? Rho u dou v by dou x plus v dou v by dou y, and pressure gradient in y direction, dou p by dou x. So put, what is the v? V it is here, v it is your x y square minus x square. What is v? V it is, u it is given y square minus x square. What is u? 2xy. V is equal to 2xy. So this 2 you have, put the value here, u dou u by dou x, find the pressure in the form of vector. Put this value here, find the pressure. Okay, so grade of P is I is there, I and J is there. So this, if you find the pressure in x direction, put the value, Find the pressure, that means dou P by dou X, dou P by dou F, multiply with that, you have to find the answer. So the answer you have to find. So if the answer it is given option number answer, that means grade of P. So grade of P, this is P is there. So grade of P is equal to minus 6I minus 6J. Done. Clear? Minus 6I minus 6J. So I hope you like this session, and after from the next session we have to take the more question of related to the branch of fluid mechanics for both branches, mechanical and civil, and we have to discuss the year of in the year 2021. Up to that, thank you, bye bye.